Hello friends, today we will discuss about a topic reinforced cement concrete. Reinforced cement concrete R.C.C. Now reinforced. The meaning of reinforcement means to improve or to add some strength to existing. Now here existing is compressive strength of concrete. Compressive strength of concrete. But concrete is very weak in taking tension. Concrete is very weak in taking tension. So to improve in tensile strength of concrete, as its tensile strength is only 10% of its compressive strength. Remember, tensile strength of concrete is only about 10% of its compressive strength. So, to improve tensile strength of concrete, reinforcement in the form of steel bars are provided. Steel bars may be of Fe 250, that is mild steel, or Fe 415 or Fe 500. These are known as tor steel. Fe 415 and Fe 500 is known as tor steel. Now this is necessary because whenever there is a tension in a member, suppose let us consider a beam. Suppose this is a beam and it is loaded with say UDL. Now it will be subjected to sagging bending moment like this. Due to sagging bending moment, suppose this is the like this. At the top there will be compression, at the bottom there will be tension, and if you provide only concrete, due to the tension at the bottom it will get cracked, the structure will fail. So reinforcement is required, especially on tension side. Now let us consider the stress distribution diagram and strain diagram for a simply supported beam subjected to sagging bending moment. Remember the chapter of bending stresses in beam in the subject mechanics of structure. In that, we will consider a cross section of a beam. Here the width of the beam is say B, then overall depth is D, and steel bars are introduced on tension side, say AST, area of steel, and the center of this steel bar from the top, the it is say small d, which is known as effective depth. whereas this capital D is overall depth. Now the stress diagram will be like this: compression at the top, tension at the bottom. This will be neutral axis. This is compression at top, tension at bottom. This is a stress diagram, and the strain diagram will be like this. Here we are using steel bars on tension side. So we'll call this as epsilon SU. Strain in steel ultimate. U stands for ultimate. S stands for steel. Strain in concrete ultimate. This is say X, that is the depth of neutral axis. This is D. So this distance is D minus XU. This X. This is D. This is D minus XU. I will call this as XU is ultimate. U for ultimate. Now, what is the value of maximum strain in steel and maximum strain in concrete? The maximum strain in concrete is given as 0.0035. Who gave this? The IS code, IS 456. See, this is the maximum strain in steel. Maximum strain in steel and maximum strain in concrete. 0.0035. These are the pictures directly taken from IS 456 2000. So, in that IS 456 2000, in limit state of collapse flexure, assumptions made in theory of bending are given in clause 38. So, in that it is mentioned that maximum strain in steel is Fy upon 1.15 ES plus 0.002, and maximum strain in concrete is given as 0.0035. Now, in this strain diagram, using properties of similar triangle, what I can write: XU upon 0.0035. See, these two are the similar triangles. XU upon 0.0035 divided by maximum strain in steel is given as I told you 1 Fy upon 1.15 ES. This epsilon SU Fy upon 1.15 ES plus 0.002. So D minus XU upon Fy upon 1.15 ES plus 0.00. Now let us consider Fe 250. For Fe 250, Fy is equal to 250 Newton per mm square, and Es as 2 into 10 raised to 5 Newton per mm square. This is modulus of elasticity for steel. Now let us substitute the values of this Fy and Es in this equation. So what I will get, Xu upon 0.0035 is equal to D minus Xu upon Fy 250 upon 1.15 into 2 into 10 raised to 5 plus 0.00. Now let us calculate this. 250, 1.15 divided by 2. So here I will get 0.88 Xu is equal to D minus Xu. So 0.53. So take Xu on this side, 1.88 Xu is equal to D. So Xu is equal to 1 upon 1.88 D, that is Xu is 0.53 D. This is the design constant for Fe 250 for depth of neutral axis. Design constant for Fe 250 for depth of neutral axis. Now here there are another two grades, Fe 415 and Fe 500. For this Fe 415, substitute the value of Fy as 415 Newton per mm square, and for Fe 500 substitute the value of Fy as 500 Newton per mm square. Es is same, 2 into 10 raised to 5, same for all the cases, and find the values of the neutral axis constant for Fe 415 and Fe 500. So as a homework, what you will do, grade of steel, complete this table, grade of steel and Xu in terms of D. So grade of steel, first Fe 250, we found it as 0.53D, and Fe 415 and Fe 500, what is the design constant in terms of D. So complete this table as a homework. So this completes our today's lecture, finding neutral axis constant, design constant. Okay, thank you very much.